Okay, this lecture is going to go through sections 12.9 through 12.11, sound intensity and beats. So the sound intensity produced by a point-like source that radiates uniformly in all directions is given by the formula there, 12.13. Intensity is going to be equal to the power outsourced divided by 4 pi r squared. A logarithmic intensity scale is usually used to measure the intensity level, beta, of a sound wave. So we've got beta is equal to 10 decibels times the log of the intensity divided by some reference intensity, chosen to be 10 to the minus 12th watts per meters squared. And this is going to be your unit for intensity, decibels. When two sound waves of slightly different frequencies interfere, alternating constructive and deconstructive interference produce beats. That can be really annoying sometimes if you are in band and somebody is really out of tune, or trust me, you'll hear it at that point. The beat frequency is going to be the difference between those two frequencies. So you can see here, you've got two frequencies that are out of phase with each other, and then you can see where the beats are defined, where they're completely out of phase down to where they're completely out of phase. Looking at that as a wavelength, that counts as a beat. So let's go and look at each of these sections individually and kind of see what they have to say on the subject. As you know by now, sound can travel in several different types of materials. If we describe sound waves as sinusoidal waves, they're going to have a frequency, amplitude, wavelength. Human ear is going to be sensitive to waves in the frequency range of 20 hertz to 2000 hertz. Now that's going to vary depending on actually whether you're a boy or a girl, and it's also going to depend on age too. That's going to change quite a bit. But we also use the term sound for similar waves with frequencies above and below the range of human hearing. If it's above, obviously ultrasonic. If it is below the range, then infrasonic. Sound waves may also be described in terms of variations of pressure at various points. In a sinusoidal wave in air, the pressure fluctuates above and below atmospheric pressure, with a sinusoidal variation having the same frequency as the motion of the air particles. The maximum variation in pressure above and below atmospheric pressure is called the pressure amplitude, or Pmax. Microphones and similar devices usually sense pressure variations and not displacement. Measurements of sound waves show that in the loudest sounds the human ear can tolerate without pain, the maximum pressure variations on the order of 30 pascals above and below atmospheric pressure, which is 1.013 times 10 to the 5th pascals at sea level. If the frequency is 1000 hertz, the corresponding amplitude is about 0.012 millimeters. So the displacement amplitude of even the loudest sound is extremely small. The maximum pressure variation in the faintest audible sound, a frequency of 1000, is only about 3 to the times 10 to the minus 5th pascals. Corresponding displacement amplitude is quite small. So for comparison, the wavelength of yellow light is about this, and the diameter of a molecule is about this. So the ear is an extremely sensitive organ. So if you take a look at the human ear, you've got the auditory canal, you've got the tympanic membrane. Remember, no sharp objects here. Then that leads into the middle ear bones. And then you've got the cochlea. And within the cochlea, you've got several different what appear to be hair-like stuff, but it's also fluid-filled. So the motion of the cochlear fluid is then imparted to the cochlea's specialized hair cells, and then the resulting nerve impulses are transmitted to the brain. That's kind of neat. So let's go to section 12.10, sound intensity. All right. Sound waves transfer energy from one region to another. So we define the intensity of a wave as the time averaged rate at which energy is transported by the wave per unit area across a surface perpendicular to the direction of propagation. That is, the intensity is the average power transported per unit area. So the intensity of the faintest sound wave that can be heard by a person with normal hearing is this. So that's sort of where we set the bar. The average total power or energy per unit time carried across a surface by a sound wave equals the product of the intensity at the surface and the surface area. The average total sound power emitted by a person speaking in an ordinary conversational tone is about 10 to the minus fifth watts, and a loud shout corresponds to 3 times 10 to the minus 2 watts. So, if all the residents of New York City were to talk at the same time, the total sound power would be about 100 watts, equal to the electric power requirement of a medium-sized light bulb. Yet the power required to fill a large auditorium with loud sound is considerable. The intensity at an individual point is proportional to the square of the amplitude of the sound wave and also proportional to the frequency of the wave. So, power emitted by a sound source represents the energy per unit area that is being carried away from the source with the sound waves. If it has amplitude A and frequency F, then the power is proportional to the square of the amplitude and the square of the frequency. So if the amplitude of a sound wave is doubled, then the power will be quadrupled. Similarly, if the frequency of the wave is increased, then the power carried by the wave will increase as the square of the frequency. Simplest source of sound is a point source that emits its power uniformly in all directions. Then the intensity at a distance r from the source is inversely proportional to r squared. So here's our formula that we discussed earlier. The average intensity through a sphere with a different radius, R2, is given by a similar expression. If no energy is absorbed between the two spheres, then the power must be the same, and therefore you can equate the two. And then you can see the relationships there between the intensities and the radii. So because the ear is sensitive over such a broad range of intensities, the logarithmic intensity scale is usually used. And this is what we come up with. Again, we've chosen this as our reference, and the log denotes a logarithm to the base 10, and remember it's not the natural log. The units are in decibels, abbreviated little d, big B. A sound wave with an intensity I is going to be equal to this, and has an intensity level of 0 decibels. This level corresponds roughly to the faintest sound that can be heard by a person with normal hearing. The intensity at the pain threshold, about 1 watt per meter squared, is about an intensity of 120 decibels. And if you are at different types of events, you can see how the decibels stack up. So you got several problems there that you can go through. I encourage you to do so. Now let's go on to section 12.11, beats. So now we're going to be talking about interference. Let's look at superposition of two waves with equal amplitude but slightly different frequencies. This can occur when two guitar strings with slightly different frequencies are sounded together, or when two organ pipes that are supposed to sound exactly the same pitch are slightly out of tune. What you hear from two sound waves with slightly different frequencies is a slow pulsing or beating sound called beats. So, consider a particular point in space where waves overlap. The displacements of the individual waves at this point are plotted as a function of time here. Total length of the time axis represents about 1 second, and the frequencies are 16 and 18 hertz. You wouldn't think there's a lot of difference there, but here we are. Applying the principle of superposition, We add the two displacements at each instant of time to find the total displacement at that time. And at certain times, the two wavelengths are in step. And their maxima coincide and their amplitudes add. But as time goes on, they become more and more out of step because of their slightly different frequencies. Eventually, a maximum of one wave coincides with a maximum in the opposite direction for the other wave, and then they cancel each other and the amplitude is 0. The resulting wave looks like a sinusoidal wave with a varying amplitude that goes from maximum to 0 and back. In this example above, the amplitude goes through 2 maxima and 2 minima in 1 second. Thus, the frequency of this amplitude variation is 2 hertz. And the resulting variation in amplitudes are beats, and the frequency with which the amplitude varies is called beat frequency. So the beat frequency is going to be the difference between the two frequencies. If the beat frequency is a few hertz, we can hear it as a wave or pulsation of the tone. So we can show that the beat frequency is always a difference between the two frequencies. So suppose F1 is larger than F2, and then the corresponding periods are going to be that T1 is going to be less than T2. If they start out in step at time t is equal to 0, they'll be in step again at the period of the beat. So such that the first wave has gone through exactly one more cycle than the second. Then let n be the number of cycles of the first wave. Then the number of cycles of the second wave is going to be n minus 1, and then you've got these relationships. So we're going to solve the second equation for n, substitute it back into the first, and then this is going to be the period of the beat, and the reciprocal is going to be such as this. That's a fundamental definition. So if you take this and turn it on its head, you find the frequency there, 1 over T1 minus 1 over T2, and then you come up with that. So that's kind of neat.